Let me start by asking you something. Have you ever wondered how large enterprises, banks, global companies, service providers, connect dozens or even hundreds of locations securely, reliably, and without relying on the public internet? The core challenge: moving traffic without chaos. How does traffic move between headquarters, branch offices, data centers, and cloud environments without turning into chaos? That's exactly what we're unpacking today. Welcome to Bluehat Cybersec Academy. The modern enterprise reality: networks without walls. You see, modern enterprises don't live in one building anymore. They operate from headquarters, branch offices, data centers, and cloud environments, often spread across cities or even continents. And all of these locations need to communicate with each other, not just occasionally, but constantly. And they need to do it securely, reliably, and predictably. Introducing the solution MPLS Layer 3 VPNs. That's where MPLS with Layer 3 VPNs, commonly called L3 VPNs, comes into the picture. Today we're going to walk through what MPLS actually is, how MPLS labels work, what L3 VPN really means in the real world, and how enterprises use all of this to connect multiple sites securely. No heavy jargon, just clear concepts, the kind that actually stick. So let's start at the foundation. MPLS stands for Multiprotocol Label Switching. At a high level, MPLS is a smarter and more efficient way to move traffic through a service provider's network. In a traditional IP network, every router along the path looks at the destination IP address and decides where to send the packet next. That process repeats at every hop. With MPLS, things work differently. Instead of repeatedly inspecting IP addresses, the network uses labels. These labels tell routers exactly where the packet needs to go, and that small change makes a big difference. So, why do labels really matter? Well, what you get is faster forwarding, more predictable paths through the network, and far better scalability as the network grows. A simple way to remember it is this: IP routing happens at the edge, and label switching happens in the core. Now, let's talk about those labels because they're the heart of MPLS. An MPLS label is a small piece of information that gets added to a packet when it enters the MPLS network. This label sits between Layer 2 and Layer 3 in the packet, which is why MPLS is often described as a Layer 2.5 technology. That label contains a few key fields. There's the label value itself, which determines the forwarding path. There's quality of service information used to prioritize traffic. There's a flag that tells the router whether this is the last label in the stack. And there's a TTL field to prevent routing loops. So, once a packet has a label, forwarding becomes very straightforward. At the entry point, a label is pushed onto the packet. As the packet moves through the provider's core, each router swaps the label for a new one. And when the packet reaches the exit point, the label is popped off before the packet is forwarded to its destination. What's important to understand here is that core routers don't care about IP addresses at all. They simply read the label and forward the packet accordingly. That's what makes MPLS fast, efficient, and highly scalable. To really understand how this all fits together, we need to look at the roles different routers play in an MPLS network. At the customer site, you have the customer edge, or CE router. This router runs normal IP routing. It connects the enterprise network to the service provider, and it has no awareness of MPLS whatsoever. Next is the provider edge, or PE raaoutrs. This is where MPLS really begins. The PE connects customers to the MPLS cloud, applies and removes labels, and maintains routing information for each customer. Then, deep inside the provider network, you have the provider core, or P raaoutrs. These raaoutrs only switch labels. They never see customer IP routes, and they never interact directly with customer networks. So this separation of roles isn't accidental. It's actually what allows service providers to build networks that are secure, efficient, and capable of supporting thousands of customers at scale. Now, this brings us to the idea of MPLS Layer 3 VPNs. An L3 VPN, or Layer 3 VPN, allows a service provider to offer private IP networks over a shared MPLS infrastructure. Multiple customers can use the same provider backbone, but their traffic remains completely isolated from one another. From an enterprise perspective, it honestly feels like having a private wide-area network. There's built-in security, seamless connectivity between sites, and no exposure to the public internet. That isolation is what makes L3 VPNs so powerful. And, the technology that makes that isolation possible is something called VRF, or virtual routing and forwarding. A VRF is essentially a separate routing table on a PE router. Each customer gets their own VRF, which means their routes are kept completely separate from every other customer's routes. Because of this, there's no route leakage between customers. Overlapping IP address spaces are allowed, and, traffic stays fully isolated from end to end. In most designs, one VRF represents one customer, and without VRFs, MPLS L3VPNs simply wouldn't work. So what actually happens when traffic flows through an MPLS L3VPN? Let's walk through it at a high level. Traffic arrives from a customer site at the PE router. The PE places that traffic into the correct VRF. Then, 2 MPLS labels are added to the packet. So let's talk about understanding the 2-label stack. The outer label is used to move the packet across the provider's core network. The inner label, on the other hand, identifies the specific customer VPN. As the packet travels through the core, routers only switch the outer label. And when the packet reaches the destination PE, both labels are removed, and the packet is forwarded toward the destination customer site. From the customer's point of view, none of this complexity is visible at all. They just experience stable, reliable connectivity between their locations. This is where MPLS really shines in enterprise environments. Imagine for a moment an organization with a headquarters, multiple branch offices, and a centralized data center. Each of these sites connects to the service provider's MPLS network. Once connected, all sites can reach each other automatically. Routes are exchanged without requiring tunnels between every location, and the design scales cleanly as new sites are added. This model is often referred to as any-to-any connectivity, and it's one of the biggest reasons MPLS became so widely adopted. Even today, enterprises continue to rely on MPLS L3VPNs, and for good reason. Traffic is isolated inside the provider network and never touches the public internet. Performance is predictable, with controlled latency, jitter, and packet loss. Quality of service allows voice, video, and critical applications to be prioritized. And new sites can be added without redesigning the entire network. Compared to traditional IP routing, MPLS offers better scalability, faster forwarding, built-in traffic engineering, and native support for multi-customer isolation. That's why service providers continue to depend on it at scale. And while SD-WAN has become extremely popular, MPLS is still very much relevant, especially for financial institutions, large enterprises, and mission-critical or latency-sensitive applications. In fact, many modern networks combine MPLS and SD-WAN to get the best of both worlds. So let's bring it all together. MPLS with L3VPN is a proven way to connect enterprise sites securely, reliably, and at scale. By understanding MPLS labels, L3VPN architecture, and enterprise multi-site design, you now have a much clearer picture of how large networks operate behind the scenes. And once you understand the logic behind it, the entire model starts to feel surprisingly simple. Thanks for watching Bluehat Cybersec Academy. If this session added value to your learning, give it a like, share it with someone who's building their networking fundamentals, and subscribe for more practical cybersecurity and network engineering content. Drop a comment below. I'd love to hear how you're applying these concepts or what topic you'd like to see next. Until then, keep learning, stay curious, and I'll see you in the next one.